All right, welcome. This is week 1. Oh, there is a skunk in my neighbor's yard running through their field right now. What a hilarious interruption. I've never actually gotten to see it. Welcome, everyone. This is week 1 of the Principles of Biology live stream. My name is Hunter. I am a post-bac pre-med student. That means I already have an undergraduate degree, but I took these classes very, very recently. And I'm working on my own studies. So we'll be doing these worksheets every week. I'll be going through the worksheet with you. Come prepared with a copy of the worksheet. Streams are going to be Thursdays at 4 p.m. I believe I have a classmate, Christina, who will be doing them on Fridays, if that works better for you. All of the recordings from my streams are going to be uploaded to the PSU Learning Center YouTube channel immediately after. No attendance is taken. Submit the worksheets for extra credit by each week's deadline. Just make a good faith effort. You don't have to get everything right. You don't even have to have the entire sheet complete. Just get what you can out of it and submit what you have, and you will get the credit. So if you have any questions, feel free to email me. I'm going to go ahead and add this on the document here. My email is hlea@pdx.edu. And that is all the admin stuff I have. If you want to talk through problems as we're working through them, if you have questions for me, go ahead and drop them in the chat, and I will address them as we go here. Let's get rid of my face and show you the document. So again, streams are live Thursdays at 4 p.m. Recordings on the YouTube channel. No attendance. Submit what you got on the worksheets, and you'll get that extra credit. And here, again, is my email. So we're talking about evolutionary processes today, and we're going to start off with some discussion of the Hardy-Weinberg theorem and a quick reminder of what that is. Hardy-Weinberg basically asserted that genetic variation in a population will remain constant from one generation to the next in the absence of disrupting factors. For example, new alleles through mutation. So I'm going to go ahead and type that off to the side here. So let's see, Hardy-Weinberg theorem. Genetic variation in a population will remain constant from one generation to the next in the absence of disrupting factors. So with that in mind, we're now going to go through and we're going to complete these definitions here. So if evolution can be defined as a change in genes, or more appropriately allele frequencies, is it conversely true that a population not undergoing evolution should maintain a stable gene frequency from generation to generation? This was the question that Hardy-Weinberg answered independently. Sorry about the interruption there. All right, so our first definition here. Population, an interbreeding group of individuals of the same what? We're going to try using the pen tool here today. So if you're on the live stream, if you can let me know if this interferes with my audio at all. I had some troubles with that last term. So an interbreeding group of individuals of the same species. Species would be important there for this population. Next up, we've got gene pool. All the alleles contained in the gametes of all the individuals in the what makes up the gene pool, makes up individuals in the population. Genetic drift. Evolution, defined as a change in allele frequencies that occurs in what populations as a result of chance events? So the key word here is, in genetic drift, is small. Changes in allele frequencies that occurs in small populations as a result of chance events. All right, question 2. The Hardy-Weinberg theorem states that in a population that is or is not evolving, the allele frequencies and genotypes frequencies remain constant from one generation to another. So if a population is evolving, are allele frequencies remaining constant from one generation to another? That would be incorrect. So if a population is not evolving, then there's no change in allele frequencies. Everything stays the same from generation to generation. The assumption, all right, so we're on to number 3 now. So the assumptions required for the theorem to be true are listed in chapter 23 on pages 471 through 472 of your textbook and are presented here in shortened form. First assumption, there are no random what that would affect the gene in question. So these are the assumptions that we're making for the Hardy-Weinberg theorem to apply to a given population. There are no random allele frequency changes. Allele frequency changes that would affect the gene in question. Let's zoom in a little bit. Next one is there's no net migration of individuals into or out of the population. Migration. Anytime we have organisms moving into or out of the population, you're going to be introducing new alleles as they're coming in, or removing alleles that would otherwise have a stabilizing effect on that genetic diversity in the population. So migration is a big one. C, there is no net mutation. Mutation, that is the forward and backward mutation rates for alleles are the same. For example, big A goes to little a as often as little a goes to big A. So for the same reasons that migration would affect allele frequencies, mutation will of course affect them as well. D, mating is at what for the trait or genes in question? Mating is at random for the trait or genes in question. Examples of non-random mating, I'm going to put this over to the side, non-random mating would include things like, you know what, this is addressed later in the worksheet. We're going to come back to that. Next assumption, there is no selection. So there's no selection. So natural selection is a really powerful driving force of evolution, but for these assumptions to apply, there can't be natural selective pressures on specific genotypes for these allele frequencies to remain constant. So there's no selection. Offspring from all possible matings for the trait or gene are equally likely to survive. All right, so now we're on to the proof, and this is where this gets really interesting. Consider a gene that has only 2 alleles, big R, dominant, and little r, recessive. The sum total of all big R plus all little r alleles equals all the alleles at this gene locus, or 100% of all of the alleles for that gene. So we'll let P, I'm going to start highlighting our variables here. So R, and P. Let P equal the percentage or probability of all of the big R alleles in the population, and let Q equal the percentage or probability of all of the little r alleles in the population. So all big R plus all little r alleles equals 100%. Then P plus Q equals 1. 1 equals 100%. And if you set this equation equal to P, then you can solve for, excuse me, this then gives you an inequality that you can solve for either variable as long as you know one or the other. So frequencies are stated as percentages, for example 50%, and their associated probabilities are all stated as decimal fractions, so 0.5. Assume that 50% of all the alleles for fur color in a population of mice are big B black and 50% are little b brown. The fur color gene is autosomal. All right, so what percentage of the gametes in the females alone carries the B allele? So we've already said that 50% of the alleles for fur color in a population of mice are big B and little b. So since this trait isn't necessarily sex-linked, then 50%. 50% of all of the gametes in the females should carry the big B allele. What percentage of the gametes in the females alone carries the little b allele? And that, of course, would also be 50%, since we have even distribution and this is not a sex-linked trait. What percentage of the gametes in the males carry the B allele? And this would be the same. This would be the same. We know that the distribution is 50% of the alleles for fur color across the population, and it's autosomal, so it is not a sex-linked trait. So given the preceding case and all the Hardy-Weinberg assumptions, calculate the probabilities of the three possible genotypes: big R with big R with little r, and little r with little r. So we have two homozygous genotypes and one heterozygous genotype. Hetero meaning more than one. Calculate the probabilities of the three possible genotypes occurring in all possible combinations of eggs and sperm for the population. All right, so the first one has been done for us, which is very convenient. Kind of gives us a way to infer what this chart might be trying to tell us. And this is your classic Punnett square. So we have female gametes and probabilities, male gametes and probabilities. We have our different alleles. I'm going to do this in a different color. And then red will be our heterozygous. So a big R and a big R come together to make this homozygous dominant, or P sub 2 genotype. Moving over to the next block, we have big R with little r. So big R with little r. And this gives us our first heterozygote. Same thing happens here. We have little r with big R and little r with little r. Homozygous recessive. We'll do this in a different color. And this would be, I'm not used to using this the PQ notation anymore, so I have to get back in the habit of that. So that would be PQ. This is also PQ. And this would be QQ for the purpose of our equation. So because the because the offspring types represent all possible genotypes for this gene, it follows that p squared, we'll write this again off to the side, p squared plus 2pq plus q squared equals 1 or 100% for all genotypes for this gene. So this formula gives us a really tidy way of calculating what all of the different genotypes might be in the population. So using your understanding of the Hardy-Weinberg proof and theorem to answer the following questions. Use your understanding. According to the Hardy-Weinberg theorem, p plus q equals 1, and p squared plus 2pq plus q squared. So this, what I've highlighted in red here, is our 2pq. We have pq over here and pq over here, 2pq. R squared, big R squared and little r squared, or p squared and q squared. So that's what these variables kind of correspond to. Maybe we can highlight that with our color coding just to make it a little bit more clear. So we have p squared, q squared, and 2pq. According to the Hardy-Weinberg theorem, what does each of these formulas mean, and how are the formulas derived? I guess I've kind of accidentally done that by color coding this already. We're deriving these using equally probable alleles and their corresponding frequencies based on this distribution. So if you add all of the dominant alleles for a gene to all of the recessive alleles for the gene, you're going to get all of the alleles for that gene, or 100% of the alleles for the gene. And this is assuming that the gene only has 2 alleles. So all dominant alleles for a gene to all the recessive alleles for the gene, get all of the alleles for that gene. In our next equation, p squared plus 2pq plus q squared equals 1 if you combine all of the individuals that are homozygous dominant for a gene with all the heterozygotes and all of the homozygous recessive individuals for the gene. You have counted and combined all of the individuals in the population that carry that gene. So it's same story plus the heterozygotes. All homozygous dominant, homozygous recessive, and the heterozygotes you've counted or combined all of the individuals in the population that carry that gene. All right, assume a population is in Hardy-Weinberg equilibrium for a given genetic autosomal trait. What proportion of individuals in the population is heterozygous for the gene if the frequency of the recessive allele is 1%? So the recessive allele is 1%. That can be expressed as Q equals 0.01. as a decimal. So using our equation from above, all of the dominant allele frequencies plus the recessive allele frequencies should equal 1. Right? So this is solved a little bit differently here in my answer key, but I think, yeah. So in mathematical terms, we know what Q is. So P plus 0.01 equals 1. If we rearrange this, P equals 1 minus 0.01. P equals 0.99, or 99%. And this gives us our frequency of dominant alleles in the population. And if we want to apply this to our other equation, this value yeah, so we can calculate the frequency of heterozygous individuals in the population as 2pq which would be 2 times 9 times 0.01, which would be 0.0198, or 198 out of 10,000. Hopefully this is making sense to folks. And if not, I hope you'll email me about it. About one child in 2,500 is born with phenylketonuria, an inability to metabolize the amino acid phenylalanine. This is known to be a recessive autosomal trait. This is a recessive autosomal trait. If the population is in Hardy-Weinberg equilibrium for this trait, what is the frequency of the phenylketonuria allele? So 1 in 2,500. So let's start with some assumptions. Let's assume that P is the normal allele. Big P is the normal allele, and little p is the phenylketonuria allele. The frequency of homozygous little p individuals in the population is then equal to Q squared. Let me finish writing here. So the frequency of the homozygous little p individuals in the population is equal to Q squared, which is 1 in 2,500. So Q squared, it's a little clear that that's a Q. 1 in 2,500. And this is given. The frequency of the Q allele is the square root of that. Which equals 0.2. So for population in Hardy-Weinberg equilibrium for this trait, the frequency of the phenylketonuria allele is about 2%, or 2 in 100. since we have it. Part B, what proportion of the population constitute carriers of the phenylketonuria allele? That is, what proportion is heterozygous? So first, let's find the rest of our equation. So we calculated Q up in the previous class. We know that E is Q on E equals Q, and Q is 0.02. Therefore, P equals 0.98. So that's our homozygous, or that's the frequency of our dominant allele for big P. But that's not what this question is asking for. This question is asking for heterozygotes, those that have big P, little p. And these would be carriers, but who would not express the phenylketonuria allele. So heterozygotes should occur at the frequency 2pq. So 2pq. We have and for q. And now we simply solve. The frequency of heterozygotes 0.0392 or 3.92%. All right, question 4. In purebred Holstein cattle, about one calf in 100 is spotted red rather than black. The trait is autosomal, and red is recessive to black. All right, so we've added a few complicating factors in here. So what is the frequency of the red alleles in the population? So if one calf out of 100 is spotted red, then the frequency of the recessive red genotype is 1 in 100, not q, but q squared. So to get q, then we just take the square root, which would be 1 in 10, or 10%. So Q is the frequency of the red alleles in the population, not necessarily the cows with red spots, but the frequency of that allele. Part B, what is the frequency of black homozygous cattle in the population? So homozygous again, P squared. Now we've got a value for Q and Q squared. And let's see what we can punch in here. So P squared. Oh, interesting. This is an interesting way to set this up, and I don't know that I would have solved it this way, but this is definitely faster. Hmm. Yeah, okay, I accept that. um, every once in a while with these answer keys, we're presented with a solution that is far more straightforward than the way I might have learned to do it in the first place. And this is one of those moments. Cool. Let's move on to part C. We'll come back to it if we need to. What is the frequency of black heterozygous cattle in the population? So heterozygotes, again, is represented by 2. Going back to that original calculation here. So we've got the value for Q1 and the value for P was 10. To 18 and 100. All right. Question 5. Assume that the probability of a sex-linked gene for color blindness is Q equals 0.09. And the probability of the normal allele is P equals 0.91. This means that the probability of X chromosomes carrying the color blindness allele is 0.09, and the probability of X chromosomes carrying the normal allele is 0.91. What is the probability of having a colorblind male in the population? What is the probability of having a colorblind male in the population? So remember that males have only one X chromosome. I'll write this off to the side here. XY biological male, biological female. Color blindness is a sex-linked gene that is found on the X chromosome and not the Y chromosome. And as a result, a male has a 0.09 probability of having the X with the color blindness allele and a 0.91 probability of having an X with the normal allele. So it's as written here. For sex-linked genes, males display the allele frequency at 0.09%. There are no other confounding factors here, and so males will express the gene at 0.09. For sex-linked genes, males display the allele frequency at 0.09. What's the probability of a colorblind female? Unlike males, females have 2 copies of the X chromosome, and as a result, they display the genotype frequency for genes. As a result, they display the genotype frequency for genes on the X. A colorblind female is homozygous recessive for the colorblindness allele, and the frequency of the homozygous recessive genotype is Q squared. 0.09 squared is 0.0081, or 8 in 1,000 roughly. So far less frequent. Oh boy. So so in our previous questions, we were talking about autosomal characteristics. There was no sex linking to that gene, and the reason that there are so many more colorblind males than there are colorblind females is because there's only one chromosome. There's only one X chromosome to really carry that recessive gene in males. When you have double X's, then you can think of it as more squares in your Punnett box. There are more variables introduced, and so the frequency of that allele carrying through is much, much, much lower. Okay. Can you hear me okay? I've opened a window to try and get some airflow, and I've picked the computer up off the table so that hopefully it doesn't cook and our connection stays stable. How are we doing right now? Okay, fantastic. The demands on the equipment are precipitating the need for new equipment. So we've got a solution on the way that should be set up in time for week 2. So I apologize for the difficulty there. If it happens again, just spam the chat and get my attention. All right. We've got another 22 minutes. We're going to get as far as we can in this worksheet. All right, next up we've got, back to our worksheet. The ear tuft allele in chickens is autosomal and produces feathered skin projections near the ear on each side of the head. This gene is dominant and is lethal in the homozygous state. In other words, homozygous dominant embryos do not hatch from the egg. Assume that in a population of 6,000 chickens, 2,000 have no ear tufts and 4,000 have ear tufts. What are the frequencies in the normal versus ear tuft alleles in this population? So, important details here. This gene is lethal in the homozygous condition. The gene is also dominant. Therefore, homozygotes that are produced do not hatch and do not appear in the population, so they're not contributing to the numbers that we have here. The population contains 4,000 heterozygous tufted chickens and 2,000 homozygous normal chickens. Because we don't know how many eggs were laid, or we don't know how many eggs did not hatch, or how many of these contain homozygous tufted chickens, we need to calculate the allele frequencies by assigning alleles to the existing population. So how can we do that? I'll do my best to type this if I can. So we've got 4,000 tufted chickens. We'll call that 4,000T. We've got 2,000 normal chickens. Let's see. What's the best way to do this? We're going to do a rough Punnett square here. So we've got 4,000T, and we've got another 4 there, which gives us 8,000 total little t alleles and 4,000 total big T alleles. So for our allele frequencies, let's see, how do we want to do this here? Let's see. Jeez. When I said spam the chat, I didn't mean this. Oh, come on. All right. Back to our allele frequencies. We know that we have 4,000 individuals that are heterozygous and express that tufted gene. So we have 4,000 of the big T tufted dominant alleles. We also have, am I reading this right? Yeah, we have 6,000 chickens total. 2,000 have no ear tufts, and so they must each of those 2,000 must have 2 of those little t alleles. So 4,000, and the heterozygous also carry 2 of those. Is that right? Yeah, so in 6,000 chickens, we have 12,000 alleles. 8,000 plus 4,000 is 12,000. So 4,000 and 12,000 is about a third, so 0.33 is a third. So allele frequency T equals 0.33. Little t is 8,000 and 12,000, or 2/3, which is 0.66. Whew, that was choppy. I apologize, gang. All right, how can one determine whether or not a population is in Hardy-Weinberg equilibrium, and what factors need to be considered? Sorry, we haven't even answered the previous question yet. What are the frequencies of the normal versus ear tuft alleles in this population? No? Okay, yes. Yes, so we've got our frequencies of alleles now. How can one determine whether or not a population is in Hardy-Weinberg equilibrium, and what factors need to be considered? So to determine that a population is in Hardy-Weinberg equilibrium, you need to be able to calculate the numbers of individuals in the population that are homozygous versus heterozygous for alleles. Need to know homozygous versus heterozygous individuals. Need to know number of to determine whether a population is in Hardy-Weinberg equilibrium. If you know the frequencies for each genotype, you can calculate the allele frequencies, as we did in question 6 here. So if frequencies of each genotype are known, then allele frequencies can be calculated. Then, given all of the allele frequencies, you can calculate the genotype frequencies that would be expected in the population if the population were in Hardy-Weinberg equilibrium. So given allele frequencies for each genotype, you can calculate, let's see, Given the allele frequencies, you can calculate the genotype frequencies that would be expected if the population were in Hardy-Weinberg equilibrium. Then compare these values to the known values for the population. So in reality, this is really difficult to do, because if alleles show dominance, then it's hard to distinguish the homozygous dominance from the heterozygotes. And as a result, we tend to look at the frequencies of homozygous recessive phenotypes in a population, because if this remains relatively constant from one generation to the next, then we use it as evidence to assume that the population is in Hardy-Weinberg equilibrium. Since that dominant allele is going to override a recessive allele if present, then it's really difficult to tell sometimes when that recessive allele is present, which is why the homozygous recessive is kind of your benchmark for determining that. All right, question 8. Is it possible for a population's genotype frequencies to change from one generation to the next, but for its gene or allele frequencies to remain constant? And explain by providing an example. The short answer is yes. There's a number of ways this is possible, and here's one. So earlier, I started to write out examples of non-random mating and stopped because I knew this question was coming. So one example is inbreeding. If we assume that inbreeding has occurred in two populations of mice, for example, then in one population the mice have become homozygous, so big A, we'll say, at a particular gene locus. And in the other population, the mice have become homozygous little a, at that gene locus. Equal numbers of little a, and big A mice happen to migrate to a new habitat, and then the frequencies of the big A allele is 50%, and the frequency of the little a allele is 50% in the new population. And all possible combinations of mating of these mice could easily be listed, and the frequency of those alleles would not change. So each of these matings should occur with equal probability. So let's see here. How do I want to type this out for y'all? So genotype frequencies would change from one generation to the next, but the allele frequencies would remain constant. Another way to think about this is, in a population that is inbreeding, that has no other inputs, then the number of alleles that you have is the number of alleles that you have. And those can get non-random mating in this way leads to a higher occurrence of homozygous dominant and homozygous recessive as a result. So, all right, thank you all for your patience with the background noise and the technical difficulties. I have solutions on the way. They've been coming and been delayed over and over. I was hoping to have it all taken care of before this first stream launched, but we get what we get, so we'll do our best. Hopefully next time is better. Thank you all for your patience. Fill out those worksheets, submit them to, I think it's the Google form, get that extra credit, email me if you have questions. See you next week.